So what we're going to talk about today is the fundamental kind of central physics of how basically cloud droplets and rain droplets form. In this course, I don't have a chance to talk in detail about ice. As I mentioned, it complicates things enormously. It's extremely interesting and fun, but we would need a whole course. I'm already pushing things to try and squeeze the cloud physics down into 1 or 2 lectures, should we say. So, but I think it's nice to have an understanding of what's really going on the small scales when clouds are forming before we talk about how these are represented in climate models. Okay. So, let's have a look. So what we're going to do is, in general, when you're considering cloud physics, what we're concerned with is the changes of phase in particular between, for example, water vapor and liquid, or indeed freezing of liquid droplets to ice, or maybe the direct formation of ice from the vapor stage, although it's never directly from the vapor stage when homogeneous processes are actually concerned with ice. So changes of phase between vapor, liquid, and ice. All I'm going to talk about, and I still haven't worked out why that happens. Is this right? Have I lost it? View. Presentation. See? I don't know why it does that. I don't improve, do I? So all I'm going to talk about today is the formation of the liquid droplets from the vapor stage, and then in very brief terms, the second process, which is the transformation of small cloud droplets into rain. But for that, I'm not going to have a mathematical treatment, just a descriptive treatment. So as I say, the ice phase processes and the complications even of the liquid droplets falling, I'm not going to talk about in detail because we only have 6 lectures. Okay. So before we start, I have to introduce some of the nomenclature. So the descriptive terms that we use when we're describing cloud physics. So we tend to split up droplets and crystals into what we call distinct modes. And the reason for this will become clear. The reason is that if we look at the probability of finding droplets of a certain radius, okay, so we want to look at the PDF, probability density function, of how many droplets we find in different radius bands. What we'll find is you don't just have a smooth spectrum of drop radii, okay. The processes that act to form rain or cloud droplets are highly nonlinear, and what they tend to do is they tend to favor one of 2 states. Okay, this is highly schematic, but what you'll find is you tend to find either that droplets are in a very small radius category, okay, or that they're in a very larger raindrop kind of size category. So what we can do is we can treat these ranges of radii as bulk modes, just like we did for the radiation. Okay, we could have treated every single frequency very finely, separately, almost line by line. But what we did is in our simple model, we divided up all of the wavelengths into the solar and the long wave, because that was convenient. There was a reason to do that, because most of the radiation from the Earth was transmitted, or emitted, sorry, in a certain range of wavelengths. And then from the Sun, another range of wavelengths. So it's the same thing here. We have certain modes that we can divide droplets up into. So what I'm going to talk about today really is only the first 2 modes, which are called cloud drops and raindrops. Okay, familiar terms. But we'll see why that they can be divided quite easily. So ice, as I said, is very complicated. This is the only picture of ice. It was just, I added this just to highlight what I was mentioning last week, that ice crystals can have a whole range of different forms and shapes, needles, columns, flat plates, all of which have different radiative properties. They have different fall speeds, and so on. But I'm not going to talk about that in any detail. What I'm going to be talking about today is cloud droplets, and this is a schematic to kind of highlight the differences between these should we say, size categories. So a typical cloud droplet has a radius on the order of 10. The units here are microns, so meters times 10 to the minus 6. Okay. So a cloud drop is on the order of 10 microns, compared to a raindrop, which is on the order of 1,000 microns. So they've tried to draw this to scale. So you can see that the raindrop almost seems flat compared to the cloud droplet, because we have a difference of 2 orders of magnitude in radius. Okay. And then these up here are trying to illustrate borderline cloud droplets and rain droplets. And we'll see that these are not very stable. These are quite rare, these sizes. So in the atmosphere, droplets will tend to be either in this category of size or this category of size. Okay. Now there's something mentioned here which will crop up in this lecture, so bear this in mind. This says a typical condensation nucleus, 0.1 of a micron. So 2 orders of magnitude smaller. So I'm going to come back to that. Just kind of flag that now in your memory. Okay. Now this is a quick recap of the discussion I put on the board. So I'm going to go over this quite quickly. It's just to remind you of the basic definition of the saturation. But we can do this quickly because we explain this carefully on the board. Remember, if we had a body of water, that was the cartoon I drew on the left. Water vapor molecules that manage to break the hydrogen bonding leave the surface in a process of evaporation, which, if you remember, was dependent on which parameter? Temperature, very good. So the higher the temperature, the more the thermal agitation, and the faster the evaporation rate. And then the opposite was the condensation, which depended on the vapor pressure. Okay. So this was just to recap what we discussed last week. So we had this discussion, and we defined the saturation vapor pressure, which is when we had an equilibrium between the evaporation rate and the condensation rate, if you remember. And so when we have that equilibrium, the volume of air is said to be saturated. So we're exactly saturated when the evaporation rate and the condensation rate are equal. Okay. Now, we've used the example here of a planar body of water, but we're going to use the same concept when the body of water is actually a droplet of water as well. But then we have a little bit of modification to do with this definition, which we're going to talk about next. Okay. So this is just a recap, remember, because the evaporation, it depends on temperature, and the condensation depends on the vapor pressure. Then the saturation vapor pressure depends on temperature, and temperature only. Not quite true. Okay. We're going to find out that there are 2 other aspects that can modify this relationship a little bit. Okay. Now, when the vapor pressure exceeds the saturation vapor pressure, okay, in theory there's no reason why this shouldn't happen. What that state is actually called then is supersaturated. So we have a vapor pressure exceeding the vapor pressure. Now, what actually happens, I mentioned last week, is then cloud droplets quickly form. So we're going to learn why this is the case, okay? Because it's not obvious that this is the case. So just to illustrate, I schematically drew this on the board. This is just, again, to emphasize that this saturation vapor pressure as a function of temperature is a highly nonlinear relationship. And that is quite important when it comes to mixing in clouds. In fact, just as an example, does anybody know why in the winter here, it doesn't happen very often in Trieste, but in England in the winter, often in a cold morning, when you go outside, when you breathe, you have this like cloud of condensation. Okay. Does anybody can think of a reason why that occurs? The difference of temperature, and it's also related to the nonlinearity of this curve. Okay, just quickly, this is a bit of an aside. I don't want to run over with the lecture. But when the air in our lungs is very moist. In fact, it's very close to saturation. Okay? And it's also warm because we're mammals, so we have a warm body temperature. So if we imagine on this graph, this is temperature, okay? And this is the saturation vapor pressure. The air in our lungs is warm, so to the right, okay? And it's very close to 100% relative humidity. It's very warm. So probably on this graph, schematically, we could put a X there. It's not exactly on the saturation line if it's not 100% humidity, relative humidity, but it's probably a small distance underneath the saturation because it's very humid. Okay. Now when we move outside, the air around us is much colder in the winter. Okay. So it's colder, and maybe it's not, if there's no fog around us, it's also subsaturated. It's not at the ES. So maybe we can draw a point like this if it's quite humid. Now, when we breathe out, what happens? We're breathing out air from our lungs. And does it just stay homogeneous? If I release a blue gas here, and I come back into the room a week later, will the blue gas just be here in the corner? No, it will mix, no, in the room. Same when we breathe out, there's mixing with the air around. And so the temperature, it depends how much of the air from my lungs mixes with how much of the air around. But let's just assume for simplicity that half-half, equal mixtures. Okay. Temperature is roughly linearly mixing, so the temperature of the mixed parcel will be halfway between the two, okay, if it's half and half. And then also the saturation, so the vapor pressure is also approximately linear mixing. Okay, so we can draw a straight line between these points. And if it's half on the temperature, half on the humidity, the final parcel will have a temperature here, the mixed parcel, and a humidity here. Is it above or below the saturation line? Above. So we form droplets in the air, like a small cloud. In Trieste, you very rarely see it because the air here, I've drawn it badly, is much drier in the winter because often it comes down from the mountains. It arrives very dry with low relative humidities, and therefore the mixing line, I've drawn it very badly here, normally falls below. So even the mixed parcel is still subsaturated. Okay. It's one of the things you notice between the climate here and in the UK. Okay. So, as I said, if the relative humidity exceeds 100%, then cloud droplets form. But this is due to the curvature of these droplets. So we're going to see why this is now. Okay. But before I start that, I want to introduce very quickly surface tension. Okay. Compared to a lot of other liquids, water has a very high surface tension. So what do we mean by that? Well, due to the intermolecular attraction, we have a difference between what's happening in the middle of a liquid and what's happening at the surface. So if you imagine one of these molecules here, essentially there's hydrogen bonding, so intermolecular attraction from all directions around. So you have essentially an equilibrium. This is not the case on the surface. Here we only have attraction in one direction. Okay. So what that tends to do is that means that there's a net force that tries to bring in the surface towards the body of the liquid. Okay. And so there has to be a surface, but the net result of this, should we say, imbalance, this asymmetry in the forces, is that you tend to try and minimize surface area. Okay, and that's what creates surface tension. So insects, for example, it's particularly strong in water because of the hydrogen bonding, can walk on water because of that. Because if you have a surface of water, if an insect is pressing on this surface, it's making the surface longer. So there's a net force to try and minimize the surface and bring this back up. So that's what causes the surface tension. And because of this surface tension, that's why that small droplets will tend to be circular. So you have this net force, and you have basically spherical water droplets. And this is important, as I mentioned, because the saturation vapor pressure, as we defined it in our cartoon, was over a planar surface, yes? But now when we start to consider small liquid droplets, the curvature of that droplet starts to have an impact. Okay. So if you imagine, this is a little cartoon I've drawn of a planar surface. If we look at this one particular molecule, okay, it has all of these neighbors which are attracting it. So we have intermolecular bonding. And in order to escape, so the process of evaporation, all of these bonds have to be overcome, okay, in the process of evaporation. If we have a small droplet, this surface molecule now has fewer neighbors if the curvature is very high, okay. So that means the attraction from its neighbors is reduced, okay. So if we have the definition of the saturation vapor pressure, remember that's when we have an equilibrium between evaporation and condensation, will the saturation vapor pressure be higher or lower in the vicinity of a small droplet compared to a planar surface? So have a think about it for a second. So the bonding is reduced. Okay. So the energy required to overcome this bonding is reduced. Okay. So what happens to the saturation vapor pressure? Does it go down or does it go up? How many? I had some downs and some ups. Who was the down? Down, yeah? Why do you think it goes down? Do you? So if you imagine for a fixed, let's imagine for a fixed temperature, okay, which will have the highest evaporation rate for a fixed temperature? The droplet or the plane? The droplet. So we have a higher evaporation rate, okay, for a fixed temperature. So in order to have an equilibrium, we also have to have a higher condensation rate, yeah? And in order to have a higher condensation rate, what does the condensation rate depend on? Vapor pressure. So will the vapor pressure be higher in saturation or lower over the droplet? Don't be shy. Higher, exactly. So for a given temperature, the evaporation rate will be higher. In order to have an equilibrium, we need to have a higher condensation rate to balance. So in other words, the equilibrium will be formed at a higher vapor pressure. Okay. And for very small droplets, this is not a small effect. Okay. So the expression that relates the ratio of the saturation vapor pressure for a given radius r to an infinite radius, so what I mean by an infinite radius, of course, is just a planar surface, is given by this relationship. So it's an exponential, and on the top, sigma is the surface tension. Okay, so we have a value given here for usual conditions for water. Okay, this is just a constant, a gas constant. I haven't introduced this because we haven't gone through the details of the thermodynamics, but just imagine this is a constant, this is the density of liquid water. But the two things we have to note is we have an inverse relationship for, we have the r, radius on the bottom, and then also temperature. Okay. So the larger r is, the smaller this becomes. So we can basically approximate this to A over RT, okay? Is that clear so far? So if we have a small radius, then this becomes larger, and this ratio becomes larger, yeah? And the larger this becomes as this approaches infinity, when this becomes infinity, then essentially these two are the same, of course, because that's what we expect. Okay. And if we just do a very simple Taylor expansion, this can be actually approximated. I'll use this later for simplicity as 1 over A divided by RT. the main relationship to remember, it's just this form here. So A is just incorporating the constants that we introduced here, the sigma, the RV, and the rho L, okay, and the 2, of course. Okay, so the smaller the droplet, the larger the saturation vapor pressure is. So if we have a droplet in an environment that is subsaturated, so subsaturated, remember, means that E is less than ES. Does the droplet grow or shrink? Right, let's have a think for a moment. So we have a droplet that's in an environment, and E is less than ES of R. So it's subsaturated. Does the droplet grow or does it shrink? Or is it stable? So E is less than ES. So we have a droplet, and the vapor pressure is less than ES. Okay, exactly. Because remember, when E equals ES, we have an equilibrium between the condensation rate and the evaporation rate. So if E is less than ES, the condensation rate is reduced, and therefore we have a net loss. The evaporation rate exceeds the condensation rate. Yes? Okay. And likewise, if E is greater than ES, then the droplet will grow. Okay, because we'll have net condensation. So there'll be a net diffusive flux of water vapor towards the droplet. Okay. Say again? Well, the formula here is just telling us what the ratio is of the saturation vapor pressure over a curved surface compared to a planar surface. Okay, it's not telling us about the diffusive equation for the actual rate of the growth. So all I'm looking at here now is just a descriptive term. Remember, the picture you always need to keep in your mind is this one. Okay, this is the picture this depends on. So, and the definition that the saturation vapor pressure is when you have an equilibrium. So if the pressure here is less than the saturation, then this condensation rate will be reduced. Is that clear? And so you have a net evaporation. Okay, and the droplet then will reduce. The amount of water in the liquid state will reduce, and the vapor pressure will increase until an equilibrium is re-established. Or, in the case of a cloud droplet, the cloud droplet simply is exhausted and disappears. So we no longer have a liquid water droplet. Okay. Where was I? So, if we are to form an initial droplet, let's imagine we have clear sky conditions, okay, and we form an initial droplet by a chance collision. So water vapor molecules all around us now, they're flying around, and at this every single second there are collisions going on in this room. Okay, we don't see them, of course, because we're talking about the molecular scale, but all around us at the moment, water vapor molecules, as they're moving around, are crashing into each other. Okay, and sometimes when they crash into each other, there's the hydrogen bonding, and they might be linked. Okay, so there might be an attraction. So imagine, say, that all at one point we have 10 molecules bump into each other, and they spontaneously form, then, basically a very tiny, microscopic liquid droplet that consists of 10 molecules. Okay. Now, we can ask ourselves, is that microscopic droplet of 10 molecules, is it stable or unstable? So the question is, once it forms, will it stay the same? Will it evaporate? In other words, will the molecules overcome their attraction and then just fly off separately again? Or will it start to grow and form a bigger and bigger droplet? Okay. So let's imagine we have a chance collision of n molecules, 10 or maybe even 50, the more molecules bump into each other at the same time, the rarer that event will be. Because, of course, for 50 molecules to bump into each other, it's a lot less likely than for 10. And 10 is a lot less likely than for 2. So the more molecules bump into each other, okay, the initial tiny droplet will be, should we say, larger, but it's a much rarer event. So we form a nucleus droplet of a few molecules. Ciao. You only have 6 lectures, so either listen or just catch up the lessons online. But so we have a chance collision of 10 molecules, okay, and we have to ask ourselves, is it stable or not? So what do we need to look at to ask, is it stable? Does it grow or does it shrink? Say again? So let's just imagine we have a fixed temperature. Exactly. So we need to look at E, and what do we need to compare it to? ES. So we have to ask the question, is E larger than ES for a given radius, or is it smaller? Okay? But of course, this threshold value for ES depends on the size of this droplet. Okay? And so for just 10 or 50 molecules, it's going to be very small. And in fact, if you make a calculation, so for example, if you assume, here I have the example calculated for a collision of 183 molecules all simultaneously, which is a very rare event, nevertheless, this would form, this collision, a droplet with a radius of 10 to the minus 3 microns. Okay. So the initial nucleus droplet will be 10 to the minus 3 microns. And if you work out then what the effect of that curvature is, you find that ES var for a droplet of R equals 10 to the minus 3 microns is actually 3 times larger than ES infinity. It's unbelievable. What's going on here? Say, ciao. If you don't want to listen, then I prefer you. I don't know, was there a party last night or something? I can see the whole back row is just snoozing off. Or was it just too hot in here? Let's open all the windows. No. No, we can't. See, you can't leave even if you want to. Let's open this. Fresh air time. Okay. So next time you have a party, invite me as well, okay? Then I can be snoozy at the front of the class. Okay. So, so this is equivalent to a relative humidity. Is this ruining your camera now? Okay, there we go. So we'll open it at the back. You can tell Ryuna is never going to take this film. We'll have to edit all this out afterwards. It's like, cut, take 5. Okay, so this is equivalent of a relative humidity of around 300%. Okay. Now, from our experience, do we ever experience relative humidities of 300% when we have the weather forecast at low levels and so on? You know, what kind of range of values do we normally have in the environment? Yeah, 100 is about the maximum, and down to very low values. So like I said, in winter, it can be below 20%. So we never measure these kind of relative humidities. Okay. So what does that tell us? We have to have a relative humidity of 300% for this droplet to survive and grow. Otherwise, it just evaporates because of the evaporation rate. It tells us that this chance collision is not the mechanism by which droplets are formed in the atmosphere. So we have like a question that we need to answer. What is actually going on? So that's when you kind of flag back to the first slide with the droplets. It's aerosols. Okay. So aerosols in the atmosphere are present. They range in size from 10 to the minus 4 all the way up to 10 microns in radius. Okay. And they vary widely in concentrations from very polluted areas, okay, So you can have up to like 10 to the minus 5 per centimetre cubed in an urban area, so such as somewhere like London or Rome or something with lots of car pollution, for example, to much smaller values, 2 orders of magnitude less in very clean environments. So that would be something that you measure perhaps in Chile in South America, where there's not much land mass in the southern hemisphere, and you have a lot of sea area to the west, upstream. Okay. And there are both natural and anthropogenic sources of aerosols. So natural aerosol would be, for example, sea salt. Okay. So when we have high winds, it increases the flux of droplets, which then evaporate and leave sea salt aerosols in the atmosphere. But there are also, of course, anthropogenic sources. So when we burn fossil fuels, we tend to leave aerosols in the atmosphere. Cars less now because they have filters, but nevertheless, they emit aerosols, biomass burning, and so on.
Okay, based on the previous discussion, does it mean that the water vapor is not a major source of cloud formation?
The water vapor is important. You'll see, we're going to discuss that next, how aerosols are actually important. So we have classes of aerosols. If they're larger than 2 microns, they're referred to as giant aerosols. The intermediate range is from 0.2 to 2. These are large aerosols. And then the smallest size is 0.2 and less. Okay? And they have short timescales in the atmosphere. If they're in the lower atmosphere, they'll get washed out by rain, or the larger ones will also just fall by gravitational sedimentation. Okay? So they have a typical lifetime of around a week, unless they're ejected really into the upper troposphere. Okay? In which case, they can travel quite long distances in the upper troposphere. Okay, so these aerosols, a subset of them can have a role in cloud physics. So not every aerosol is important, just a subset that have certain properties. Okay. So they can be hydrophilic, which means that they can interact or actually be dissolved in water. So they can form bonds with the hydrogen molecules in water. And so water molecules can actually collect on the surface of the aerosol. Okay. And so clouds can form by a process known as heterogeneous nucleation. So rather than homogeneous, which only involves water, heterogeneous nucleation means we have water and aerosols. Okay. 2 different kinds of substances. Okay. And so the aerosols that have this hydrophilic, should we say, property are known as cloud condensation nuclei. And there are plenty of them around. They're always in sufficient numbers to be present in enough numbers to be able to form clouds efficiently. So the process can be in 2 ways. Now, first of all, the CCN can be insoluble, okay, but wettable. So what that means is that the water vapor can condense on their surface, but they're not actually dissolvable. So in that case, these aerosols actually help to initiate clouds if they are of a large enough radius. So if we have giant aerosols in that category of, should we say, 2 microns or above, then this surface curvature is massively reduced. Remember I said a chance collision of 183 molecules here formed a droplet of 10 to the minus 3 microns. And here we have on the order of 1 micron. So it's 1,000 times greater. So the curvature is much reduced. And so that massively reduces the excess difference, the ratio between the saturation vapor pressure here and over a planar surface. But in order for this to be the case, you really have to have a radius, like I say here, of at least 0.2 of a micron. Really, the threshold is around a micron. Okay. And these aerosol, these large or giant, are relatively rare compared to most of the cloud condensation nuclei. So it's not to say this is not important, but it's not the main mechanism usually. because these giant aerosols are quite rare. So most of the aerosols that have a role in cloud droplet formation are actually soluble. Okay. So they're actually dissolved in, should we say, water vapor. So you can see here we have just the schematic of the water vapor molecules with the charge between the hydrogen. Basically, we got, and the oxygen, you have this orientation where the negative charges of the water vapor molecule basically line up because they're attracted to the positive charge of the sodium, Na, in sea salt, as an example. Okay. So as, for example, sea salt is dissolved, it spreads out within the, so it's well mixed within the water vapor. And this also has a role in offsetting the curvature effect. Why is that? Well, the reason is that if we have these other aerosol molecules dissolved in a liquid water droplet, as well as being in the internal body of the droplet, some of the surface locations will also be occupied by the aerosol molecules. So this was our molecule in question, an example molecule of water vapor on the surface. And now, from its neighboring locations, one of these, should we say, locations is occupied by a sea salt molecule, should we say. And so we have fewer water vapor molecules, okay, with the strong inter-water vapor bonding. So the net bonding is reduced by the replacement of a water vapor molecule by an aerosol. So what does this do to the vapor pressure? Remember, the curvature effect increased the vapor pressure. So what does this do to the vapor pressure? How many of the sites on the surface are occupied by water vapor molecules? So the point is here, before we had 1, 2, 3, 4, 5, 6, 7, 8 molecules on the surface. Okay. And then by replacing some of these surface sites, how many water vapor molecules do we have on the surface? 1, 2, 3, 4, 5, 6. So 2 of them have been reduced. So the number of water vapor molecules on the surface of the droplet has been reduced. Okay. So does this reduce the evaporation rate or does it increase it? So before we had 8 molecules that could actually overcome the bonding. It reduced because we have fewer sites occupied by water vapor molecules. Okay. So we have basically 6 out of the 8 sites with water vapor molecules. So now the possibility for evaporation is reduced. If all of these surface sites were occupied by aerosol, there would be no evaporation at all. There would be no water vapor molecules on the surface, because remember, it's only the surface molecules that can overcome the bonding and escape, unless the droplet is boiling, of course, which is not the case in the atmosphere. So by replacing some of these sites with aerosols, okay, then we reduce the probability of evaporation because we have fewer water vapor molecules on the surface of the droplet. That's right. So there is a change in the bonding, but nevertheless there is attraction, as we saw on the previous slide, between the sodium and the water vapor molecules. So although there is a difference in the bonding strength, the principal mechanism, so I wanted to mention that, but the principal mechanism is dominated by the fact that you're reducing the number of surface sites occupied by the water vapor. Okay. So the bonding changing is a kind of secondary effect. So this primary effect of basically reducing the number of sites occupied will also impact the saturation vapor pressure. And we can derive that effect by saying, well, what is that effect actually related to? It's going to be related to the number of sites on the surface that's occupied by water compared to the total number of sites. And so if we assume that the amount of solute, because remember, if we have a droplet, we have a certain amount of solute dissolved, and that droplet will either grow or shrink. So the water vapor can change by the evaporation or condensation, but the aerosol content stays fixed. And we also assume that the aerosol is well mixed, so it's homogeneously mixed within the droplet. So therefore, if we assume that it's well mixed, then the proportion of sites occupied will be just simply related to the ratio of the number of water vapor molecules divided by the total number of molecules. So the water vapor molecules plus the solute molecules, okay, which is approximately 1, if we just rewrite this in this form, and we can just do the expansion and take the first order terms, it's 1 minus ns over nw, okay, where we're assuming that the number of solute molecules is much smaller than the number of water vapor molecules. So in a droplet, if we assume that the aerosol is fixed, the number of water vapor molecules is related to the volume of that droplet, of course. And so it's related to r cubed. And therefore, we can say that this proportion, 1 minus n over nw, if we assume that this is fixed, we can say that this is equal to 1 minus b over r cubed, and b is a constant that depends on the aerosol type, its mass, okay, and also takes into account the pi term, of course, from the volume relationship, okay. So we have 1 minus b over r cubed. So we had two effects that changed the saturation vapor pressure. We have the curvature, okay, which had the 1 over r sensitivity, and we have the solute effect, which has a 1 over r cubed. So what this means is that 1 will dominate for smaller droplets and 1 for larger droplets. So we can put these together, okay, and so if we add those two effects together, the curvature effect and the solute effect, we have 1 minus b over r cubed, x to a over rt, which if we use that Taylor expansion and combine them and ignore the second order effects, so the effect of the r and the r cubed, we have a 1 over r4 here, which we're going to assume for small radius we can just ignore the r4 term. So if we just take the terms up to r cubed, we have this as approximately 1 plus a over rt minus b over r cubed. Okay. Well, indeed, an aerosol that's involved in the formation of a liquid water droplet, if that liquid water droplet then is converted at a future time into a rain droplet and then falls out of the atmosphere, that aerosol is removed. You're completely correct. And likewise, many aerosols that are in the path in the subcloud layer, as the raindrop falls, they're actually scooped up and washed out. That's the other loss term. But at the same time, you have emissions from the sea surface, emissions from cars, emissions. So we have this balance, a very fast turnover of high emissions and a high loss. So if we were able to suddenly turn off all emissions of aerosols within a week or so, the atmosphere loading of aerosols would drop off very quickly. And that's why, for example, I'm not going to talk about it much in this course because I don't have time, but one of the factors that offsets CO2 that actually causes a negative feedback to climate warming is actually one of the direct effects of aerosols. So aerosols if they're changing quantities, will have an effect on clouds, I will talk about here. And they also have a direct radiative effect. So if the aerosols, for example, absorb solar radiation, they will change the radiative budget. And so, for example, one of the aspects in the 1960s where there was a cooling, they think that might be caused by the fact that loadings of aerosols with like the big boom in industry was increasing rapidly during the 60s, and that actually had an offsetting cooling effect compared to the carbon dioxide. And then as industry is cleaning up, then aerosol loadings are actually tailing off. So sources from China are increasing, but in Europe, for example, aerosol emissions have actually gone down. The person to speak about that, who's really an expert, is Fabian in the office next to mine, if you're interested to learn more about aerosols. I don't know if has he taught on this course yet? No, he hasn't. So Fabian in the office to the left of mine, next to the bar, is the coffee bar, is an expert on the aerosol side of things, if you want to learn more. So we can put those two effects together, which is done in this diagram here, which is known as the Köhler curve. Okay. So what this diagram is showing is on the x-axis, it's a schematic of radius, droplet radius, okay? And then on the y-axis, we have the ratio of basically the saturation vapor pressure of a droplet of radius r and a given solute content, okay, compared to just a planar surface. So, I'm sorry, the book that I took this from has slightly different notation, so I was using ES open brackets infinity here. And it has two dashed lines, okay, and then we have this one marked here with a horizontal straight line. So when we have one here, this means that the saturation over the droplet is the same as over a planar surface, yes? Okay. And so we have two dashed lines, x a over r, okay, and we have a 1 minus b over r cubed. So this, remember, was the curvature effect, which increases the saturation vapor pressure. And this was the solute effect, which decreases the saturation vapor pressure. Okay. And so we can put those two together, as we did, and that was that relationship, sorry, here, or this one here, in fact. And we find this solid line. Okay. Now, it looks like it's almost parallel at the end, this solid line, but as we go out to very large radius, what's actually happening to this line? It tends to 1, yeah? Because at very large radius, the curvature effect is no longer important, because a very large radius is like looking at the Earth's surface. It looks like it's flat, okay? And also the solute effect is also unimportant at very large droplet sizes, because then the amount of aerosol dissolved in that very large droplet is very small. So it only occupies a very tiny number of surface sites. So it doesn't impact the evaporation rate anymore. But what we see is that at very small radii, because of the r cubed term, the solute effect dominates. Okay. And this is quite important. And we'll see why now. So let's imagine, I'm going to just quickly draw this graph again, so it's easier here on the board. So we have, this is our 1, okay? And so we had basically a solute impact. I should do my best. And then the slower curvature impact. And then we have our Köhler curve, which looks like this, okay? Well, when the droplet first forms, okay, then you have a certain, should we say, initial droplet size, Haze droplet. Let me talk through this first, and I think that'll become clearer, that question, afterwards. So, yes. because it's fixed, so if we have like an aerosol and we have a droplet, if that droplet is unstable and it grows, then it grows by diffusion of water vapor. The condensation rate exceeds the evaporation rate. So always keep that picture of the condensation and the evaporation. So if it grows into a larger droplet, the aerosol that's dissolved is still the same.
Yeah, but is it possible to have such kind of cloud? I mean, is it stable? Is one, I mean, like,
Well, this is the point of this discussion now. So if we start off with very dry conditions, then we have aerosol in the atmosphere. We increase the relative humidity. So we could increase the relative humidity by adding water vapor, or we can change another parameter, which is the more common way in which clouds form in the atmosphere. So we can increase the water vapor, but how else can we change the relative humidity in the atmosphere? Temperature. So we can make the vapor go up, or we can make the temperature go down. And in fact, the most common way which clouds form in the atmosphere is when air moves upwards, it cools during its ascent, the temperature drops, and so the saturation vapor pressure is dropping due to the drop in temperature. And so the relative humidity is increasing. Okay. So if we have the relative humidity increasing, what happens is we get to a certain stage where the humidity is high enough that the aerosol then starts to form a wetted particle. So it starts to attract, there are enough water vapor molecules such as the collision, so you actually form a very small solute droplet, okay, which is on the order, it's a submicron droplet. And these, I don't know if you've heard this term before, are known as Haze particles, okay. So they're submicron, basically, solute, very tiny droplets where it's just aerosol that's wetted. So it has on its surface, it's dissolved maybe, a small dissolved droplet, but where the amount of water is quite small. I mean, the aerosol and the water are relatively equal in terms. And so that occurs already when the relative humidity reaches a value of around 78%. Okay. So these are not cloud droplets. These are submicron wetted solute droplets. Okay? And they, for example, are what is responsible for reducing visibility in the summer. So if you noticed here in Trieste in the winter, when it's cold and very dry, you can see all of the Alps very clearly, yes? In the summer, that's extremely rare, because in the summer, it's normally warmer, but it's also much more humid. And so when the humidity goes above 78%, all of the aerosols, which are always present, become wetted and form small aqueous droplets, tiny droplets. And they basically interact with the solar radiation. They diffract it, and they make it much more hazy. So the distance that you can see is much less. It doesn't mean that there's more pollution necessarily, or more aerosol. It just simply means that the aerosol is there. It's become wetted. It's like almost like a small sponge. It's starting to swell up, okay, by attracting water. So let's imagine that we have one of these very small droplets, okay? And we're at this situation here where we're in equilibrium, okay, with its environment. So why are we forming this droplet? Because essentially, for the very tiny aerosol particles, the small radius means that you have this depression of the saturation vapor pressure. So although the relative humidity is less than 100%, remember 100% relative humidity, the way you may measure it is relative to a planar water body. Okay. However, for a very small aerosol, the equilibrium, should we say, saturation vapor pressure is greatly depressed. So once you reach this 78%, you're already in equilibrium. Okay. Now let's imagine that we reduce the temperature or we increase the humidity in the environment. Okay. So that the E, let me get rid of this arrow here, I don't want to confuse you. So we increase the humidity. So the humidity is going up from 78 to 82%. So E is here. Are we supersaturated or subsaturated with respect to this haze particle that's been formed and is in equilibrium? Supersaturated. So although the relative humidity is now 82%, so compared to a planar surface, it's subsaturated. For the haze droplet, it's supersaturated. So what happens to the haze particle? Increases. Okay. How much does it increase? Well, we can tell by this Curler curve, yeah? So it will increase in size, and we can find out how much increases because we can go up to this point and across to the graph, and then we're back in equilibrium, yeah? And I can do the same. If we increase it further, the humidity, we move up, and we reach a new equilibrium. If we increase the temperature, or we reduce the humidity, we become subsaturated, and it will shrink and reach a new equilibrium. So what we can see is that these haze particles are in a stable situation, okay, because they're in an equilibrium. And why do we say they're stable? Because if we make a finite perturbation to the vapor pressure, there's a finite response in the radius to achieve a new equilibrium. Is that clear? So if we increase the relative humidity by a small finite amount, the droplet is no longer in equilibrium, but then it grows until we reach a new equilibrium. Okay? And so we can increase again, and we reach a new equilibrium. And we can increase again, and we reach a new equilibrium. Okay. If we keep increasing the vapor pressure, eventually we reach a certain point, okay, which I'm going to mark R star, okay, at a saturation ratio, which I mark S. Saturation ratio is just simply E over ES infinity, okay, which I'm going to mark S star. Why is that a special location? Why is this radius special? Because what happens if I increase now the vapor pressure to this level, which is slightly in excess of S star? So this droplet and this haze particle here will grow, yes? How much does it grow by? So it keeps growing. It reaches this point. At this point, the vapor pressure is still in excess of the saturation. So it's still going to grow, yes? Okay. So it carries on growing. But now what happens? As the droplet is growing, the curvature effect is dominating the solute effect. So now, as the droplet grows, the equilibrium saturation vapor pressure is actually reducing. Okay, so the difference between E and ES is actually increasing. So the droplet won't only grow, but it will start to grow faster. So we have this runaway growth. Once we reach this threshold, because now the slope of the graph of the Curler curve is going down, then the droplet will just explosively grow. Okay, from its very small submicron size, so a small fraction of a micron, out to around 10 microns by diffusion of water vapor. So we can say that once the haze droplet reaches this special critical radius, it becomes activated. Okay. So we can see we have two regimes. We have this stable regime, and we have this unstable regime. In the stable regime, the solute effect is dominating, and so we have these stable haze particles. But if we actually reach this critical R star, S star, okay, then it's activated. Now I've drawn this like this. This is like an exaggerated curve, but this S star under normal circumstances is on the order of around 0.5%. Okay, so it's around this value. Okay, And it depends on the solute, the amount of solute, and it also depends on the updraft speed. I don't want to complicate the matters too much today. So it can be 0.03. It can also be up to 0.101. Depends on the thing. But it means, essentially, it's very close to this value here. And so we activate cloud droplets at relative humidities that are normally less than 101%. So if we can measure relative humidities at warm temperatures exceeding 100%, but that excess is very small. Okay. So that's basically what I say here on this slide. So as I say, it's haze particles that are responsible for reducing basically visibility. And in summary, what I haven't mentioned is that in over land areas, the number of aerosols is much higher, but a smaller proportion of those aerosols can act as CCN. Okay? But nevertheless, you still have many more CCN over land than over oceans. Okay. So the proportion over ocean is around 10 to 20%, where it's only 1% over land can act as CCN. However, remember, we have almost 1 to 2 orders of magnitude greater sometimes CCN over land. It can be on the order of 5 to 10 times greater typically over land compared to oceans. CCN was the abbreviation for cloud condensation nuclei. Cloud condensation nuclei. Okay. So remember, sorry, it's good that you reminded me because I don't think I introduced the abbreviation when I introduced the term, which was, I need to change that in the notes, actually, good point. So this is the subset of aerosols that can act as cloud, should we say, condensation nuclei that can act to form cloud droplets. So they have the properties of being hydrophilic. Okay. So just to recap at that point, before I talk about the final parts of the microphysics, what we've learnt then is that we have two effects from the aerosol and from the curvature, okay? And that we have this critical threshold at which droplets are activated. Now, once they are activated, this diffusional growth is very fast up until basically cloud droplet sizes, which is what I'm going to talk about now. And also that this excess is quite small. It's a fraction of a percent. So when we talk about climate models, we'll see that some of the assumptions are, just to simplify this, this aspect of S star is not modeled, for example, in climate models. They assume that if the relative humidity reaches 100%, liquid droplets will form. Okay. The other thing I should mention, because I'm not going to talk about ice microphysics here, is that ice is quite a lot more complicated. And the reason why is that you can have quite large excesses of relative humidity with respect to ice. So in the ice phase, you can have supersaturation because ice nuclei are much rarer. And so in ice clouds tend to form, in general, by haze particles forming, okay, which then immediately freeze. But these haze particles form at supersaturations with respect to ice, which are quite large. Anyway, you don't have to remember that, but all I wanted to do is emphasize the fact that ice processes are quite a lot more complicated, and this discussion here about the fact that you don't have large supersaturations is not the case for ice. Okay, so those of you continuing with the course next year, I talk about the ice microphysics in more detail. Okay. So when these droplets are activated, these haze particles are activated, they grow very rapidly by diffusion of water vapor towards the droplet. Okay. But the change in radius basically decreases as the droplet actually grows, because as the droplet grows, the surface area is growing. And so what you find is, and I'm not going to go through the equations here in this course, but if you derive the equations for the radius growth rate, that it starts off very rapid, but as the droplet grows, the surface area grows, and therefore the rate of change of the radius slows down. If you can imagine, for a given diffusive flux, then the larger the droplet, then the diffusive flux is spread over a larger surface area, and therefore the rate of change of the surface area will decrease. And so all I give here is this table, just to give you an indication of this. So this is the time taken for an initial activated droplet of, say, like 0.1 of a micron to grow up to a 1 micron size, to grow to a 5 micron size, to grow to a 10 micron size, and 100 microns. And so what you see is that in order to grow to 1 or to 5 or to 10 microns, okay, it's quite rapid. So to grow to 1 micron, we just need 1 second. Okay, so it's very fast. To grow from 1 to 5, we need another 35 seconds. Okay. To grow from 5 to 10, it's already increasing. Yeah, there's around it's 114 seconds more. So to go from 5 to 10 microns takes 114 seconds. From 1 to 5 microns is just 35 seconds. Okay. So how do these times compare to the life cycle of a cloud? So like a storm that came over this morning, how long does one of those storms take to kind of form and dissipate? And it's more than a few minutes, yeah? It's on the order of like an hour or 2 hours. So you can see that compared to the life cycle of a cloud, this is just 1 or 2 minutes. It's very fast. In fact, the initial small cloud droplet sizes is just a few seconds. And in fact, this is why, if you think about it, one of the questions that the Victorian age kind of scientists were concerned with as well was why cloud edges are so sharp. And this is the reason why, that once you reach this critical threshold, you very rapidly, within a second, form the micron-sized cloud droplets. And so cloud edges, when you have these cumulus, fast-growing clouds like you saw this morning, have very well-defined edges. They're not just diffuse and fuzzy. And that's because in the upward motion, as soon as you reach 100% relative humidity, then you form the cloud very quickly. So this boundary of the cloud is a very accurate contour line of the areas where relative humidity is less than 100% and the areas where the relative humidity exceeds 100%. Okay, it's marked by the cloud boundary, exactly. So we can see that we grow the 10 micron droplets in a couple of minutes. Okay, so it seems that this diffusion growth of the droplet after activation is relevant for the cloud droplets. However, in order to grow that kind of borderline, remember that graph for the different sizes. So 10 microns was typical of a cloud droplet size. 100 microns was the borderline to a rain droplet. Remember, a rain droplet was around 1 millimeter in size. Here we need 15,000 seconds. So 3,600 seconds is an hour. So we're on the order of like 4 or 5 hours here. Okay. So if it takes 4 or 5 hours to grow a borderline small rain droplet, and yet the storm this morning that came over Trieste forms and dissipates in an hour, do we think that this diffusional growth is relevant for forming rain droplets? No. Okay. So how do we think rain droplets form? Well, it's a different process. Okay. And it has to do with fall speeds. So the other aspect, and again, I won't give the equations behind this, but one aspect that also needs to be considered is the fact that droplets also have very different fall speeds. So by fall speeds, we're talking about the terminal velocity of the droplet, okay, where the gravitational force is balancing the drag on the droplet. Okay. And this is, again, highly nonlinear. And the reason why it's highly nonlinear is, well, what do you think? As the droplet gets larger and larger, what tends to happen is the drag increases and it starts to deform the droplet. Okay. And so the drag regime changes. Also, the drag regime changes because as small droplets with slow fall speeds, you have very laminar flow around the droplet. Okay. And as the droplet increases, okay, and so the terminal fall speed becomes larger, what tends to happen then is you start to get eddies form within the wake of the droplet. Okay. And so this causes an increased drag, these vortices behind. You want the flow to be as smooth as possible when you design a car, because if the flow over a car is very smooth and laminar, you have very low friction drag on the car. If the car, the old days, the cars were much more boxy, like this, and so the flow was not very smooth, and you got all of these trailing vortices, which eventually means you just get like a turbulent wake downstream, and the droplet deforms. Okay. In fact, rain droplets, we said I gave a typical size of 1 millimeter, but if you measure the raindrop spectrum, you never really measure raindrops in excess of 2 millimeters. Why do you think that is? Why is the maximum size for a raindrop only about 2 millimeters? 2 to 3. Because? No? Yeah, it's to do with the terminal velocity, but when the droplets get larger and larger, so the terminal velocity gets larger. So I started to give you a hint here where you start to get a deformation of the droplet. What do you think happens when it goes too fast? Exactly. So the drag gets too large, okay? It overcomes the surface tension, and the droplet breaks, okay, into smaller droplets. So droplets that are too large essentially will break up. However, if you're driving along the costiera and you go through the galleria, there's like a tunnel. Often when you're driving under the tunnel or you're driving under trees, you get much bigger drops, plop, that go on the windscreen. Why is that? Why is it that raindrops can be only 2 millimeters and yet drops that fall from a tree are much larger? Yeah, exactly, because the tree is much lower, so they haven't reached their terminal velocity yet. If the tree were very, very high, then even drops that fall from a tree will break up during their descent due to the frictional forces. Okay. So, again, I'm just giving you the numbers here. We don't go through the mathematical derivation due to time restrictions, but essentially what you see is that the terminal fall speed is highly nonlinear as a function of radius. So you can see that a droplet of 1 or even 10 microns has a fall speed of a fraction of a meter per second. So we have 0.01 meter per second for a 10 micron droplet. So how does that compare to typical updraft speeds in turbulence? So remember I said about these deep convective storms, they can often have air that's moving up at 5 or 10 meters per second. Okay. Even shallow clouds near the boundary layer will be moving over at, say, 0.5 meter or 1 meter per second updraft. So when you come into land in your plane and you go through that bumpiness, that's air that's moving up and down. It's driven by the heating at the surface at around 0.2, 0.5, maybe 1 meter per second. So compared to 1 meters per second, this is quite a small value, yes? So in fact, in climate models and weather forecast models, generally we ignore this fall speed and we assume that cloud droplets of 10 microns are in suspension. So they don't fall, they just move with the flow. Okay. However, this is not the case, we can see, for raindrop sizes. So 1,000 microns, 1 millimeter, we have a terminal fall speed of around 8 meters per second. So this is fast compared to typical atmospheric motions, and so these droplets are falling. So we can see that the droplet fall speed, for example, for rain droplets is much faster, and small droplets is very small, so they're in suspension. What do you think is another important outcome of this differing fall speed? What do you think is happening inside a cloud? So in a cloud, let's start off. Do we have, do you think, all of the droplets exactly the same size when we form a cloud? No. So if we imagine a cloud, we can see that some of the droplets are being formed at lower levels, high levels. We have some of the air that's being mixed in from the side that's maybe causing some droplets to evaporate because it's reducing the vapor pressure. So inside a cloud, we're likely to have a spectrum of different drop sizes. Okay. So if we have different drop sizes, those different drop sizes will have different fall speeds. So if we have different fall speeds, what's going to be occurring inside the cloud? Let's imagine like a situation on the motorway. We have cars, they go at different speeds, yeah? Now, if we were to drive on the motorway at different speeds with our eyes closed, okay, what's going to happen very quickly? There's going to be a crash, yeah? Okay. So what do we think is going on inside the cloud? Collisions between droplets, because they're all falling at different speeds. Okay. When the droplets collide, what do you think can happen? Form a unified droplet, yeah, of much larger size. So, could this be a mechanism that's important? Indeed it is. So, the way that droplets actually form, and again, I'm not going to go through the mathematics of this in this particular lecture course. I'm just going to talk about it descriptively, is that we have an initial size range of droplets, okay, and the larger ones are falling faster than the smaller ones, so they will scoop them up, okay. And we can derive the rate at which this occurs by just doing a simple schematic where we just imagine a homogeneous cloud of a certain size of cloud drops with a large droplet falling through. And we assume that it just scoops up everything within the cylinder of its droplet radius below it. So in a unit time, the volume that it scoops up is related to its terminal velocity multiplied by the unit time. This is this height multiplied by pi r squared. Okay. And so if we know the density of the cloud droplets, how many cloud droplets we have per cubic meter, and we know what this area is, then we can work out how quickly these droplets grow. Now, in order for this process to be efficient, we need a reasonably wide range of radii inside the cloud. Because if the cloud basically consists of droplets that are ranging between 1 and 3 micron, these cloud droplets all have very small velocities, so the difference is very small. And so the process is completely inefficient. Okay. In order for this process to become efficient, then we need to have the largest droplets of a certain threshold radius, and that radius is on the order of 20 microns. Okay. So we need to have a reasonable number of droplets inside the cloud reaching 20 microns. So if we imagine we just have, just for simplicity, a symmetrical distribution of cloud droplets, and the largest are on the order of 20 microns, it means that our mean radius is on the order of 10 microns. Okay. So if the mean radius is on the order of 10 microns, so the largest droplets in the cloud are 20 microns, then this process starts to become efficient. Okay. Now, if we go back to the diffusion process, remember the diffusion process, the larger the droplet was, the slower the rate of growth of the cloud droplet became, remember? So if we imagine this is time and this is radius, the diffusional growth started off quickly, but then it started to tail off. And it took a really long time to grow the droplet out to large radius. Okay. What about this collection? Once it starts, do you think it becomes more efficient as it goes on, or does it become less efficient? Okay, so the diffusional growth, as the radius of the droplets grow, it becomes less efficient. What about this collection and coalition process? Do we think, I haven't gone through the mathematics, but just thinking about the process, just to try and understand it. What is let's think of an analogy. Okay, so a typical situation is that we're taking, or maybe a rainstorm on the outside of a glass window, or another example is taking a shower, not with a shower curtain, but one of those glass panels. Now, have any of you ever been there in the morning, you're taking the shower, you're still pretty snoozy, like the guys on the back row are today, okay? And then you're kind of like daydreaming, you're watching the panel. Have you ever just sat there and watched the droplets? Now, the bathroom is very humid, and so the droplets tend to grow, you know, from the high humidity. And then what happens is, as you look at the screen, some of those droplets get large enough that they start to overcome the friction between themselves and the screen. So some of them will start to move down very slowly. And as they move down, they bump into another droplet, and they overcome the surface tension, and they join up with that droplet. Have you ever watched that process also on the window? And then it starts to move down a little bit quicker. And so as it moves down a bit quicker, it bumps more quickly into other droplets. And so it moves a bit quicker, and then all of a sudden, whoosh, it goes, yeah? Moves down really quickly. And then as the bathroom gets more and more humid, more and more of these droplets start to go, and they go, and they go, and they go. Okay. So you can see, as the droplet, the 20 micron droplet, moves down, maybe it takes quite a while for the first collision, but that first collision increases its size, so it moves down a bit faster, bumps into another droplet, takes up that droplet, gets even larger, so it moves down even more quickly, and then it goes quicker and quicker and quicker, and then it just falls very quickly and scoops up all the droplets, growing very quickly to a 1 millimeter size. Okay. And so the process has a kind of critical threshold where we need to be able to grow droplets to a 20 micron size in order for it to start. But once we reach that threshold, these droplets will start to go. It's highly nonlinear, and the process takes off very quickly. Okay. So you remember when I talked last week, I said about some of these big questions from 100 years ago. One of them was, why is it so difficult for clouds to rain? Okay. And the reason, now we know the answer, because we have two processes that are required in order to get a droplet from an activated haze droplet all the way out to a rain droplet. And those two processes are both highly nonlinear, but in different directions. So we have one process that grows droplets very quickly to 10 microns, but then takes quite a while to get up to 20 microns. And we have another process that once you reach 20 microns, then quickly moves the droplet into the 1,000 micron gap. So now, at the beginning of the lecture, I talked about the two modes. Now you understand where those two modes come from, because if we have just the first process of activation occurring, but we don't get to that second threshold, then we leave the droplets in the 5 to 10 micron category size, you see. And it's only when we reach the second threshold that we can then shift suddenly all of the droplets, or many of the droplets, into this second category of 1,000 microns. And so we have these two processes acting in clouds, and they can leave the droplets in one state or another state. So if we look at the distribution of droplet sizes, that's why we have these two modes of either cloud droplets or rain droplets. And again, open brackets, that's a kind of a side statement. Ice also complicates the picture because a lot of the rain, like today, has ice involved. Okay, so this picture of the raindrops forming is only in the processes that occur in warm rain clouds, and often ice is playing a role, especially in mid-latitudes. Okay, but nevertheless, the two of the fundamental processes for forming raindrops that fall through the Earth are based around this diffusional growth from activation, and then the collision coalescence process. Okay. So the take-home message from the lecture, and it really is a little bit of a whistle-stop tour because I'm trying to give you just a flavor of the cloud microphysics in one lecture. But the thing to remember when we talk about the models, the climate models, is when we come to the climate models, we start to talk about, and the weather forecast models, much larger spatial scales. Whereas those models are sensitive to the assumption of the microphysics, because we know that the clouds interact with radiation. We know that the rain processes will change the hydrological cycle. And these hydrological cycle and the, should we say, the processes that are going on inside the cloud, this formation of droplets, are basically related to the microscale. So we have this imbalance of scales. And this is the reason why we need to try and parameterize these processes in a simplified way in these climate models, because we can't represent, of course, the motion of every single cloud droplet or every single rain droplet. And I just wanted to put the caveat here of the ice processes. Okay. So that's the main, should we say, summary there. So try and remember the processes and understand the Köhler curve, the activation, should we say, pathway of cloud droplets, and then the second process of how raindrops are actually forming. And remember this, this schematic where the diffusional growth is very efficient at small radii, but then the collision and collection process is efficient once we reach a critical threshold, which is having droplets of 20 micron in radius. Okay.
Okay, because we have different types of clouds, how does this process influence the various types of clouds?
Well, the formation of cloud droplets inside, should we say, clouds at low altitudes, at warm temperatures, essentially follows this pathway, this process. The one thing I haven't had time to talk about today is that the aerosol number, which is then the cloud condensation nuclei concentration, so the CCN concentration, is related to the amount of aerosols. And that will change the properties of the cloud. So in this very simple picture here, let's imagine we have two clouds for the moment, okay, shallow clouds. One is forming in air over land, over London, with high quantities of CCN. And the other cloud is forming over very clean air, so over the ocean in the southern hemisphere, with very few CCN. Okay, so we have the two clouds, one with high CCN and one with low CCN. And let's imagine the temperatures are the same, the relative humidity is the same during the cloud ascent. So the only difference is the CCN concentration. Which of the two clouds will have the largest mean drop size? The one over London or the one over the southern hemisphere ocean? southern hemisphere. Why?
Because this, as we said, water, if it were blended, then it would go on all of them, so it would be less.
Exactly. So the polluted air mass, or the air mass with more aerosols, so therefore more cloud condensation nuclei, the water is the same, but it's distributed among a higher number of CCM. Okay. So if you have the same water, but you have more droplets, then the mean size of the droplet will be smaller, yes? Okay. So which of the two clouds do you think is more likely to rain? The one over London or the one over the southern hemisphere? Southern hemisphere. Because the mean droplet size is larger, and therefore we expect the chances to have 20 micron droplets to be larger. And in fact, I remember a few years back I was lucky enough to be able to travel through like South America, so I was traveling up through Patagonia. And the thing that was really struck me is you would have this very shallow cloud systems come over, like shallow fair weather cumulus, and they may be only a couple of kilometers deep. And you would find that these clouds would come over and they would just make a small shower that lasted maybe 1 minute or 2 minutes. It would just rain a little bit and then it would stop immediately. And it really struck me because that kind of cloud in the UK or here would never rain. You'd see the cloud of that depth and it would go over, but it wouldn't form any precipitation. And yet on the southern tip of Argentina, because the air is extremely clean and you only have a low number of CCN, those clouds was almost like on some of these cartoons you watch when you're a kid and you have the person walking along, the little cloud comes along and then it moves off. It was like that, and it seemed really strange because in my experience before, you would never expect that kind of cloud to rain. I remember somebody saying, "Oh, do you have an umbrella?" I said, "Oh, I don't need an umbrella for that." And then it just started raining immediately, and it was really surprising. So that, for example, is how the aerosol can affect different clouds. But the underlying physical process of activation of droplets, diffusional growth, and then collision to form raindrops is the same, whether the cloud is moving up very rapidly or whether it's a very like a stratiform cloud. The only difference is that if the air is moving up very rapidly, then you can get a larger spectrum of droplets, and so you're more likely to form rain. But I don't want to get too much into the complications here without going through the underlying the equations to explain those differences. But the aerosols is one example to picture those differences.